Thank you. First, let me remind you some results of the previous lecture. We considered out-of-time autocorrelator, also called OTOC, for a semi-classical system. And in the semi-classical limit, the out-of-time autocorrelator grows. It actually grows exponentially with the Lyapunov exponent, or twice the Lyapunov exponent if we consider the commutator. And then the growth stops. It saturates when quantum effects become strong. And that happens at the Ehrenfest time. Today we will consider so-called large N models. These are purely quantum models with a large parameter N, a large number of degrees of freedom, and 1 over N will play the role of the Planck constant. So quantum effects will become important at a certain time called scrambling time, and it is similar to the Ehrenfest time. So we consider models where there are many sites, N sites, and those sites can be spins or Majorana degrees of freedom. Let's begin with spins. And let's write the general Heisenberg model. In a large N model, all sites are coupled to each other. So it's a system with all-to-all interactions like this. But all the interactions are pretty small and random. So we say that the average value is 0, and the second moment will be J squared. J is some parameter with dimension of energy, and divided by n for the right scaling in the thermodynamic limit. And the distribution can be Gaussian. It's not very important whether it's Gaussian or some other distribution. And the model is just constructed such that it can be solved easily. Actually, the spin model is not so easy to solve. There are still problems. Although one can use a mean field approximation, one has to deal with the problem of a spin in a fluctuating field, because we have to do a mean field in time. And if we focus on some site J, the other side produce fluctuating magnetic field acting on site J. And we have to consider the spin dynamics in that field. To make the problem completely solvable, one can go in two directions. One direction is replace spins with fermions, and the SYK model does that. And the other direction is to introduce randomness in time. And I'll show you in a moment how it's done. But first, let's consider the dynamics of this model, in particular, the operator growth under this evolution. So if we begin with some operator A of 0, 0 means time 0, and A can be, for example, sigma 1 x. It doesn't really matter whether it's x, y, or z. then we can consider the evolution of this operator in time. Actually, the operator itself is fixed, but we'll expand it in a different basis. The basis is time dependent. So A of 0 equals sum over A, some wave function that depends on A and T, sigma A, and A, last time it was called a Pauli string. It's A1 through AN. The assignment of labels to those sites, and labels can be either 0 or X, Y, or Z. So there is a trivial label and one of the three Pauli labels. And last time it was called Pauli strings, but we can also think of this string as an arrangement of bacterial cells or bugs on this graph. For example, there can be bug of type X sitting on site J, on site 1, for example. This is how we start. And after some time, this bug or bacteria can divide and occupy other cells, but some of the bacterial cells can die because of overpopulation. And this is just an analogy, but one can write an exact equation. So this is a possible configuration that will occur after some time. And the equation of motion for the Heisenberg model, and actually for large class of models, is this. The time derivative of the wave function of this bacterial colony equals sum over D, some effective Hamiltonian, and its matrix element begins with psi B, and it should be minus I in front. And the matrix element can be written like this. It's 1/2 trace of sigma A, the Hamiltonian commutator with sigma B. And, this is the formula for the matrix element. So we have quantum dynamics of those bacteria, and this is still a complex problem, but if we introduce randomness in time, then it becomes really simple. So randomness in time is called Brownian type model. Due to the analogy with the Brownian motion. And in this case, we have J that is time dependent, and for the same curve of J and K, there is a short range correlator like this. Some coefficient K times the delta function. And in this case, we can be sure that the matrix element is diagonal. we average it over the random noise. So if we consider psi A, psi B, star, average, it's some, let me call it P. P is a probability times delta AB. So the matrix element of the bacterial colony becomes diagonal in their configuration. And one can write down an equation for P sub A as a function of time, and the equation is quite similar. There is some transition probability from B to A times P sub B. So instead of the Schrodinger equation, we obtain a Markov process. And we can actually solve this problem completely, assuming large n. Of course, we need to derive those transition probabilities. And they derive from this and averaging according to that equation. But let me just state the result. So the result is, suppose there are two sites, J and K, and site J is empty, and site K has a bacterial cell. There are three types of bacteria, X, Y, and Z. Suppose it's X. Then it can go with probability K over 2 per time. This is the probability per time, per unit time. And another probability, K over 2 per unit time. So actually it's K over 4. And 1/4 appears because we have spin operators, but here we use Pauli matrices. So this is how 1/4 appears. So the transition probability between this configuration and the YZ configuration and the ZY configuration is K over 4. And one can go the other way around. So we can interpret it as one of those bugs dying due to overpopulation. And this is assuming a certain type of bacteria, type X. If we average over types, if we assume that all three types occur with equal probability, we can renormalize those transition probabilities. But the forward transition, so one side is empty, the other side is occupied, and there is a forward transition with probability K over 4 per unit time, and now both sides are occupied, and this thing does the same, so we can combine them, just say it's K over 2. However, the reverse process will occur with a different probability, because these two types should be different for the reverse process to occur. And the reverse process occurs with probability K over 3, actually, because we need to multiply this number by 2/3. 2/3 is the probability that the two bacterial cells have different types. So there is this local process. Local means affecting only two sites. And we can turn it into the population dynamics. So let me write down the equation for the population.
Excuse me?
Yeah.
Where did the equation for psi A and psi B come from?
This equation.
Yes.
So I have not derived it, but let me just give you an informal argument. We have some coherent processes, like there are coherent transitions from state B to state A. And there are transitions to other states. Now we make the Hamiltonian rendering time, and that kills any interference. So the wave function becomes diagonal. Of course, you may ask why it is diagonal on this basis rather than a different basis. But one can show that in this particular model, it will be diagonal in the Pauli basis.
But in this equation, both amplitudes are at the same time, or?
In this equation?
No, in the above one.
In here.
Yes.
Yeah, it's all the same time. Yeah.
This happens at finite n or large n?
This equation happens even at finite n.
Is the statement that randomness in time kills interference, so we can go to talking about Markov processes in general, like does it depend on what kind of randomness in time
Yes, it is general. Yes. So let's introduce the variable u of t. It's the number of bacteria at time t. And then we can write a differential equation for u. So with probability k over 2 per unit time, a bacteria will divide, but it must have an adjacent cell that is empty. There is also some normalization problem because we have this we want to obtain the property thermodynamic limit, so we have to introduce this coefficient 1 over n for the thermodynamic limit, and we should divide all those probabilities by n. And let's do the same here. Apart from the normalization factor, we should consider the number of bacteria times the number of empty sites, because otherwise it cannot divide. And so we should write u times 1 minus u. And the normalization factors are such that they cancel in this equation. And but bacteria can also die from overpopulation. So it's K over 3, and we consider configurations. We count pairs of sites that are connected. Everything is connected. Basically, we count pairs of sites that are both occupied by bacteria. And the probability that the fraction of such sites in the big graph is u squared over 2. And I can write it like this: K over 2 times u times 1 minus 4/3 times u. So the coefficient in front of u squared is minus 2/3, and it appears like 1/2 from here, minus 1/2 from here, and minus 1/6 from the second term.
Question.
Yeah.
So the number of bacteria is not conserved in time. So is this because you moved away from unitary dynamics? Like, this random coupling, or is this not related?
The probability is conserved in time, but the number of bacteria is not conserved in time even if the dynamics is unitary, because there are processes that connect different configurations of different sites.
This is the number of bacteria at some site, or?
No, this is the number of bacteria in the whole graph divided by n. Yes.
So in some sense, this equation was right. Assuming, so it reflects only conservation probability, but we also have like conservation of the spin and the projection of the spin. Even in the case of Brownian model, does it affect in some way?
Conservation of spin. I think it affects only the result only weakly, because conservation of spin means that the projection, let's see. It's hard to see the effect of conservation of spins in this basis, because we consider products of Pauli matrices rather than sums of Pauli matrices. So there will be some weak effect, because the total spin is close to 0. It's not extensive. But that constraint is rather weak.
Now, question. Hamiltonian is written as a Heisenberg exchange.
Yeah.
Would it be the same for some other choice of Hamiltonian? It could be some anisotropic Hamiltonian, for example. Will it lead to the same picture, or?
Yes, qualitatively the same picture. At high temperatures. At low temperatures, things become quite different. But this random model can only be considered at infinite temperature. The equilibrium distribution corresponds to infinite temperature, because the energy is not conserved. Yeah.
Yeah, sorry if I missed it, but could you repeat again how bacteria are included in the Hamiltonian or this model?
Bacteria are encoded in this formula. A of 0 is a sum over some configuration A, size of A T times sigma A. So sigma A is a Pauli operator. Sigma A equals sigma A1, sigma A2, and so on. And each of these labels can be 0, means empty site, or it can be X, Y, or Z, which means a bacteria. So we have this equation for the population dynamics. Initially, there are no bacteria, then the solution will be 0. If there is a small number of bacteria initially, say 1, it will grow. Yeah.
So if I now let this model, let's say, embed it in some real space and make the range of interaction finite but large, do I expect some kind of diffusion equation for U?
Yeah.
Okay.
It will be diffusion, a nonlinear
Well,
diffusion.
nonlinear, I see that nonlinear, yeah, but I mean, I'll just acquire another diffusion term and that's it, right?
Right.
Okay.
And with the spatial coordinate, it becomes the KPP equation that describes combustion. When let's just look at this equation and understand what it means. We can plot the dynamics. And initially it's very small, then it will grow. It will grow almost exponentially, but then it will saturate. And it will saturate at 3/4, because eventually all 4 Pauli labels are equiprobable. There are 3 labels, X, Y, and Z, each occurring with probability 1/4. And the trivial label, or empty site, also occurs with probability 1/4. That's why the saturation is at 3/4. And this initial growth is and kappa, in this case, is KO2. And this is the typical behavior of an OTOC, and we can actually compute the OTOC in the same model. We can consider something like psi1 of t, psi1 of 0, sigma 1 of t, sigma 1 of 0, sigma 1 of t, sigma 1 of 0. And one can put some labels here. The exact result depends on the labels, so we can make some choice, for example, x, y, so x and y, and now sigma x 1 of 0, according to this decomposition, it's sum over a psi a of t sigma a, and let's write a as a1 and other labels. And so this thing will determine the probability distribution according to that formula. So P A1 dot of T equals psi A1 dot of T squared. And if we don't care about the other labels, we should take the sum. And if we take the sum over A2, A3, and so on, then it's some function of A1, and it's 1 minus u if A1 is 0, and u over 3 if A1 is x, y, z, assuming that all three types of bacteria occur with equal probabilities. Initially, they don't occur with equal probabilities, but over a short time period of the order of 1 or k to the minus 1, so there is an interval of length k to the minus 1 where equilibration occurs. And this formula is valid when t is much greater than k to the minus 1. So what happens in this initial time is not covered by such a simple model. We have to track the individual types of bacteria rather than their total number. But then everything is fine, and we can compute the talk as written here. And this is the sum over all 4 possibilities here. And it's 1 minus u with probability 1 minus u, sigma x has a trivial label at position 1, and we get just sigma 1y sigma 1 y plus u is 3 sigma 1y sigma 1x. So we can actually write the sum over labels alpha and replace this x with alpha. It can be x, y, or z. And if alpha is y, then this average value is 1.
Maybe we should probably replace not x but y's, because it is y's that have time evolution, no?
No, we are expanding, well,
Okay.
it's kind of backwards, but it's just a matter of convention.
Yeah, okay.
We're expanding these guys at time t.
Yeah, okay.
Sorry. Is the case that in the second quality on this border the left side independent of t but right side?
The left side is independent of t, and the right hand side, yeah, it's a good point. This is also time dependent, but this time dependent in this two things cancel each other.
Okay.
Yeah, that's a good point. So let's consider all four terms. The first term is 1 minus u, and u over 3 comes with probability 1 minus 1. It's 1 corresponds to alpha equal to x, and minus 1 corresponds to alpha equal to y. Oh, it's the other way around. It's minus 1 plus 1 minus 1. And so it's 1 minus 4/3 u. And at long times, u approaches the equilibrium value of 3/4, and this quantity becomes 0. So they'll talk. This is the talk. So we start from this line because otherwise it's difficult to compute. We have to track individual bacteria types. And we just need to plot this equation. 1 minus 3/4 of u. Initially u is small, so it's minus 1/3. And then it will approach zero. A top is often normalized by subtracting the initial value rather than writing this thing directly. We subtract the initial value, of course. We should move this up, and it will go like this.
So it is exponential growth of early time and then exponentially approaching this 3/4.
Right. Right.
How should we understand the fact that formally at early times we we have u equals to 0. So this guy should approach, it should approach 1, whereas in reality at early times it behaves as -1.
Oh, sorry. Yeah, you're right. Somehow I confused one. I thought that u was 1 at early times. No. It's at early times it's 1, and at late times it's 0. So it's doing this. This is the error.
I see kind of a problem because if I literally plug in t equals 0 there, I can anti-commute x with y, get a minus sign, and then the result is -1 at 0 time.
Right, and that's why I said that this model does not work.
So at early times there's something like this.
Yeah,
and
there's
then
something irregular. At very early times, there is something irregular.
okay.
Okay, now let's discuss where we can go and improve on this result. This result corresponds to high temperatures, and furthermore, we purposely kill interference by introducing this randomness in time. An interesting question is whether quantum coherence is important at low temperatures. And it is in fact important. We would like to consider some large N model at low temperature, and we would like this model to be exactly solvable and chaotic at low temperature. And these are hard constraints. If we just take the random Heisenberg model without randomness in time, and take it at sufficiently low temperature, the system will undergo a phase transition into a spin glass. So the Heisenberg model is no good for this purpose. The next thing to try using condensed matter analogy would be the Hubbard model. And the Hubbard model has parameters with which we can play. If the interaction is strong, it's basically equivalent to the Heisenberg model, and at low temperatures, it will be a glassy phase. If the coupling is weak, then at low temperature it will be a Fermi liquid, which is not chaotic. There is a possibility to get something interesting at a critical value of the coupling in the Hubbard model. And that is indeed a very interesting problem, but very hard to solve. So, I recall how I approached this problem. I wanted to understand the behavior of atoms at low temperatures, and I had an idea that it's somehow related to black holes. And indeed, the behavior is quite similar. One can define a talk in black holes, and it has the same Lyapunov exponent as the SYK model at low temperature. But I was just searching through the literature and found that such and constructed a model in the 1990s which has the right properties. It's ergodic at low temperature, and it's not a Fermi liquid. And this is why the SYK model is interesting, because it's a non-Fermi liquid at low temperature, and it is still exactly solvable, or solvable using the mean field approximation and some corrections to the mean field. SYK defined their model in terms of SUN spins. And that is an additional complication. The model I will show doesn't have SUN spins. The model just has Majorana sites. So let's consider this model. Now, these are not spins. These are Majorana degrees of freedom. And I want Majorana degrees of freedom so that I don't have to deal with the conservation of charge, which will be an additional complication. There is a so-called complex SYK model where the charge is conserved, and it's also solvable, but the equations are more complex. So those sites are Majorana. They have commutation relations like this. And the convention is that anti-commutator is just the Kronecker symbol. Usually one puts number 2 in front, but let me just use this convention. And the Hamiltonian is one can make those Majorana modes interact pairwise. That will not be a chaotic model. It will be a Fermi liquid at low temperature. We make them interact in groups of Q, where Q is an even number. So it will be I to the Q, and for most purposes, Q equals 4. So this is the Hamiltonian, and there is a normalization convention. The coupling constants are random with 0 mean, and the second one is normalized like this. It's Q minus 1 factorial, which will be convenient for a certain reason, and it will be clear later. Then there is J squared. J has the dimension of energy, and M to the Q minus 1 for the right thermodynamic limit. So this is a model that can be solved using mean field. Each site J interacts with other sites. For example, we can if Q is equals 4, one can write an effective interaction of chi j and this is the effective field acting on site J, and this effective field fluctuates, but we can use the Gaussian approximation for this fluctuating field, replace it with a Gaussian field, and call it xi sub J. And each Majorana effectively interacts with a Gaussian bus, which is also a Majorana operator. The effective field is also a Majorana operator. And one can calculate the correlation function for this fluctuating field, and this will be actually the self-energy of the model. But I'm skipping ahead. Let me just derive some equations rigorously.
Excuse me, there is a typo in the indices. I think like chi, k, chi, yeah.
Yeah, thank you. KLM, yeah. So we'll be solving this model at a finite temperature, and we'll use the Matsubara ferment. We'll do operators depending on imaginary time. Since the model is exactly solvable, we'll get some expressions in a closed form, and we can analytically continue them to real time. And this way we can obtain even the talk. The talk is a 4-point correlation function, and it turns out that in the limit of large n, it can be computed exactly in imaginary time, and then we can analytically continue to real times. So that will be the strategy for calculating the talk in the SYK model. There are other methods, but let's begin with this one. But of course, before we calculate the talk, we need to calculate simpler quantities like the free energy, the green function, and so on, in imaginary time. The free energy can be calculated using the mean field approximation, and it can be calculated more accurately. One can include 1/n corrections. Let me give a quick overview of results concerning the thermodynamics of the SYK model. And then we'll derive some equations. The simpler equations will be done today, and the more complex things, including the talk, will be done on the next lecture. So, let's talk about thermodynamics. That is the one to compute the partition function in its logarithm. The first question is related to disorder or random coupling constants. One can consider the problem with quench disorder, which is the natural formulation. It means that we first fix those random parameters j, and then consider the dynamics or the partition function for a given set of j, and in this case, we should take log z. This is quantity useful. And a simpler problem is the problem with annealed disorder. In this case, the weights or the probabilities of those coupling parameters will change, and a configuration of J's, which corresponds to lower free energy, will come with higher weight. This process corresponds to averaging of Z over the disorder, and then taking the weight. This is easy. The first thing requires replicas. So log Z is if we have n replicas, we can take log Z to the n and divide by n. And take n to 0. Fortunately, the difference between these two quantities is small. So this scale says m to 2 minus q, and the same scaling holds for the fluctuations. I wrote proportional 2 because there is also temperature dependence, and at low temperature the fluctuations will be stronger. If we want to include the lower temperature case, then we can consider the fluctuation of this system energy, and that will be on the order of j squared times n to the 2 minus q, which means that the fluctuation of the system's energy from sample to sample, the fluctuations due to disorder are proportional to j times n 1 minus q over 2.
How do we get 2 minus q in this?
2 minus q is the value of a certain diagram that depends on the number of replicas. Most diagrams do not depend on the number of replicas. I mean, leading diagrams do not depend. But the first diagram that depends on the number of replicas is this one. This is for q equals 4. And I'll show the leading diagrams in a few moments. This is a sub-leading diagram, and its contribution is m to the 2 minus q. And in this diagram, one can have different replica indices, alpha and beta. In the leading diagrams, there is only one replica index.
Question.
Yeah.
You said at low temperatures, if you put q equals 2, then you get like, does this mean you have quasi-particles, like, or you have Fermi liquid at photon?
Yeah.
Is that related to this? Q minus Q? I mean, like
Q minus Q.
the fluctuations are not small.
The fluctuations are not small. They're still not extensive because the free energy or the energy normally are proportional to n, and the fluctuations will be of the order of 1. So they're relatively small, but the fluctuations of the Green function will be of the order of Green function itself. Yeah.
So if I think about standard kind of glassy models as Heisenberg, which is shared with Patrick mostly, right? I know that I can kind of solve the system with mean field at high temperature phase, but then I see that the 1/n correction to the free energy, which should formally be discarded, it diverges at the transition. What is the argument that forbids something like this in this situation? So that maybe the correction scales as this, but the prefactor in front of it explodes at some final temperature.
Yeah, this is conceivable, and it requires some study. So, first one finds a mean field solution, and it doesn't show any phase transition. But then there is a question, maybe it's a false solution. Maybe there is a solution with lower free energy, but there is an even worse possibility. That it's known from glassy models, like the Sherrington-Kirkpatrick, that the mean field solution may be unphysical. They correspond to some correlations that cannot be realized physically. They may even have negative entropy. And one way to detect that is to consider a family of solutions, say, for all temperatures. And for each such solution, one can verify that the dynamics does not slow down. Because when we approach a glass transition, the dynamics slows down, and it's possible that formally we just miss this phase transition by looking at the mean field solution. But if we calculate some dynamical correlators, we do not miss it. And it happens that one can continuously connect the high temperature phase with the lower temperature phase without any bad slowdown.
So essentially you're saying that we should have solve the model, calculate some dynamical response, and see that it has no any singularities, which is
right.
a posteriori test that this is applicable.
Right. So now let's consider an expansion of this quantity or that quantity in 1/n. We can write log z expectation value, disorder average, in the form g minus 1 times j over g minus 1 times n plus g0 times n to the 0 plus g1 times n minus 1 and so on. This is an asymptotic expansion in 1/n. And according to the previous result, the first two terms self-average for 2. Which means the fluctuation of energy can be neglected. If Q equals 4, the fluctuations of energy scale is n to the minus 1. But this term is independent of n. So at least the first two terms are safe. So the next term may be sensitive to fluctuations. And now let me just write down some results of rather difficult calculations for G minus 1 and G0. G minus 1 can be written in terms of powers of 1 over beta j or T over j. So it's a power expansion in T over j. There are actually terms with fractional, even irrational powers, like something between 5.5 and 5.6 for the Q equals 4 model. So it's complicated, but let's just consider these three terms and think about their physical meaning.
These results do not distinguish between annealed and quenched averages, right?
They do not. The difference occurs in parallel. So E naught is the zero temperature energy. And if we normalize it by n, then it's minus C minus 1. This is not a very interesting quantity. Just some number. But you can also consider the entropy at zero temperature divided by n, and that is C naught. It's just from thermodynamics, because we're talking about log Z that is extensive in n. And it has this extension. And we'll return to this. It looks strange that the entropy at zero temperature is extensive. It should vanish in principle. And specific heat is 2C1.
Question.
Yes.
So this is the energy of the average ground state wave function?
Yeah, it's the ground state energy.
What does the spectrum of this model look like? Is it even like, do you even have a well-defined like ground state?
Yeah, good question. I'll show it to you. Right. To address this question, we also need G0. And as I say, it's a result of a difficult calculation, and it involves some non-trivial ideas, but the answer is G0 is minus 3/2 log, this is just 3/2, Q over J, plus constant. There is a contribution to entropy that is extensive. It's C0 times N, and G0 also gives a contribution to the entropy that is not extensive, but it is negative. At low temperature, it gives a negative contribution to the entropy. And if we formally just use this G0, then the entropy will very slowly decrease as we cool the system down, and it will become negative, which is nonsense. Which means that this formula, particularly this formula, is true for most temperatures, but not for exponentially small temperatures. When the temperature is exponentially small, something happens that makes this approximation invalid. And different things may happen. The Q4 model undergoes a glassy transition at exponentially small temperature. And, for higher Q, I believe that the discreteness of energy levels becomes important, and that's what kills the underlying approximation. But I'm not certain about high Q. Anyway, in a very large range of temperature, exponential means like J e to the minus, say, square root of n, something like that. The glassy transition happens at temperature scales like this.
But it is not seen from the comparison.
It's not seen at all. One has to analyze the validity of approximations. Anyway, let's be content that those approximations are quite good at temperatures that scale is 1 over n, which is a reasonably low temperature, where many interesting effects happen. And if we focus on such temperatures like 1 over n and even a little bit smaller, then we can use those equations and we can try to infer the density of states from those equations. In principle, Z is the Laplace transform of the density of states. It's minus Q over T, right? And that is the density of states. And if we do the inverse Laplace transform, then we get a very interesting formula, rho of E MC0. There is an exponential large factor times sinch sinch of let me look up this equation. Here. It's the square root of the energy counted from the ground state energy. So the so-called zero temperature entropy enters the prefactor. It means that the density of states remains very large at low temperatures. But it will still vanish as we go down in energy because of this factor. But to overcome this exponential large factor, the energy has to be exponentially small. And it has some analogy with random matrices. In random matrices, the density of states is just the square root. And here it's sinch of the square root.
This is for which Q?
It's for any Q.
Any Q.
Any Q greater than Q. Okay, in the remaining time, I'll show you the diagrammatic technique for the SYK model that allows for an exact solution, and in particular, it allows for the calculation of G minus 1.
So,
Yeah.
is it possible to calculate the average directly? Just because it's linear in J with a lot of indexes, and we can integrate over distribution of J's, and we'll get that's like exponential with the square of this Myron operator.
Sure. Yeah.
And
Yeah. It is possible.
Is it possible to calculate it directly?
Well, I'm going to show a direct calculation to you.
Okay.
But you'll see that although it's direct, it's not very straightforward. It just goes on and on. So, this equation is a low temperature expansion. It's valid for small t. The direct calculation is a high temperature expansion. The high temperature expansion can be done using diagrams. One can write the sum of finite diagrams, and in each diagram we can average over Gaussian disorder. And there will be a bunch of terms. So let's see. We can calculate the partition function. We can also calculate the green function. The green function is defined like this. It's minus. This minus sign is the condensed matter convention. High energy physicists don't include the minus sign, and it's actually nicer. But let me just use this convention. Yes.
Is capital T the time ordering now?
Yeah, it is the time ordering. Yeah, it's in imaginary time. So we consider times like tau and tau prime are between 0 and beta. So we can define G of tau prime as n minus 1 sum over J minus or we can put minus sign here. And in the diagrammatic technique, this will be denoted by a SYK line. This is the SYK line. And we can consider the green function at infinite temperatures, and this will be called the bare green function. The bare green function GB equals minus this to the minus 1. And more exactly, the bare green function is 1/2 sine of tau minus tau prime. It's this is an Pareto form, and this is the more explicit. So, and that should be minus 1. Now, when we calculate this green function in terms of the bare green function, we should include interactions. And an interaction can be like this. For example, a Majorana particle with label J with time tau can propagate. It will propagate right to left, but I'm drawing the diagram left to right. And there can be some interaction occurring, and due to this interaction, there are intermediate states with indices K, L, and N. Since these are Majorana particles, we don't have to draw errors. The green function is just antisymmetric in the two indices. And this occurs time tau 1, tau 2, and this is J tau prime. Okay. And the interaction vertex is this matrix element. Or rather, the coefficient in the Hilbert form. there are two coefficients with the same set of indices, and we should take the Gaussian average. So we should use Gaussian averages, like suppose we have one vertex with indices J, K, L, M, and it has non-zero Gaussian average for the same set of indices. And this dotted line should correspond to Q minus 1 factorial, Q equals 4 in this case, divided by n, with Q minus 1 times J squared.
Probably M instead of N.
M, yeah. Thank you. Now, in this case, we have to sum our internal indices. So we have to sum our K, L, M. There is this factor Q minus 1 factorial divided by, let's say, Q equals 3. Q equals 4, sorry. And there is also a symmetry factor of this diagram, because we can permute this 3 lines, and we should put 1 over Q minus 1 factorial. And this coefficient in the definition of the model is purposely chosen such that it cancels this. And the sum over K, L, and M gives M cubed, which cancels that. And this is J squared. So the result is that this diagram, we should include the dotted line as shown here. This diagram does not scale with n, it's just proportional to J squared. So the diagrammatic extension for the green function begins with the bare green function and that diagram. So in conclusion, I'll just show you a set of diagrams, and we'll work with them next time and compute something useful. So, minus G. Let me use minus G for this line. And minus G sub B for this thin line. This is minus G sub B plus this diagram, and let's put some indices here. But we have taken the sum of K, L, and F, so let me just put the times. It's tau prime, tau 1, tau 2, and we should integrate over times. And there is no symmetry factor because the symmetry factor is cancelled, and we just use the convention that the dotted line is j squared divided by n to the q minus 1. It's just a new convention that renormalizes the symmetry factors. So this way we don't have any coefficient in front of the diagram, but we can continue. There are higher order diagrams, and some of them are leading, meaning that their contribution is of the order of 1, and some are subleading. The contribution scales with 1 over n. And the next leading diagrams are these two. Turns out that one can take this sum exactly, meaning that one can derive a Schwinder-Dyson equation with a certain form of self-energy, and there will be a pair of equations, the Schwinder-Dyson equations, that can be solved either numerically or analytically, and one can calculate the actual Green function. In this limit, and much greater than 1. And one can also calculate the 4-point function. The 4-point function includes ladder diagrams. I'll show you next time. Thank you for your attention.